I would like to welcome to the Institute for Advanced Architecture of Catalonia, to the visitors, and also thanks to our community to be present in one of our amazing lecture series. I'm presenting this lecture today because I have the pleasure of introduce Daniel as a friend and also as a classmate from the How to Make Almost Anything class at MIT in 2008. Where a few of us, we were being the guinea pigs of the Fab Academy Global Program, which today has 300 students in more than 70 places in the world, and is actually the team that is working together with Ferdi in the Fab Lab. Many of you have seen this amazing group of around 30 people here at IAAC working on very intensively on learning how to make things. Our paths kind of took different directions. Now Daniel is in Carnegie Mellon University, and where he's directing a master program in computational design. You just landed, and just going to tell us about that experience, and also going to tell us about the main technological revolutions of the post-war revolutions. Is that okay? And how it is affecting maybe the interpretation of reality through computational design. So, Daniel, thank you for being here. The stage is yours. Thank you, man. Yep.
Is this on? Hello? Yeah. Okay. Yes. Thank you so much, Thomas. It's great to be here. Thank you, everyone, for stopping by. It's really a pleasure to be here. I was here maybe 5 years ago. Thomas toured me around the Institute, and it's really inspiring to see how it's grown and how the work has continued to evolve in such interesting directions. So it's really great to be here, and I'm also happy to be here discussing the work that just became a book last year, which is in part the result of a doctoral project that I finished at MIT a couple of years ago. And I'm excited to be here because it's a book that I wrote to start a conversation with people who are concerned with architectural research and who are trying to think reflectively and inquisitively about technologies in design. And I think the IAAC is exactly the right place to discuss these questions. And I think it's important to discuss technologies in design from a broader frame, in part because as we continue to imagine technological futures, we have here a robot arm, we have big laser cutters, we have 3D printers, 3D printers, data visualizations, crowd-funded projects, wearable computers, responsive environments, computational geometry, etc. A dominant image of design starts to emerge as a sort of force with its own agency, and that's something that I'm interested in discussing, because I think that this determinism can be problematic. How we talk about design and how we represent creative practices in the way we talk about architecture or about design across fields is important because it shapes the expectations of people like ourselves, people in the architectural research community. It shapes the expectations of the public about how cities get constructed, how artifacts get built, how services and products get designed. So the questions that I want to explore with you today here in this lecture have to do with that perspective. What can we architectural researchers learn from an intellectual history of the technologies that we use? Can we nurture a critical imagination of technology in design? So I will try for the next several minutes, I will try to offer some materials to start thinking about these questions and to start perhaps answering them. I will first offer a context, and then I will look at the early days of computer-aided design systems. In doing so, I will try to keep an eye open for the links between engineering, mathematics, architecture, and design, which is the convergence that I think is responsible for us being here today. So, in the early days of what we have defined as the information age, the political scientist and economist Herbert Simon advanced a view of design as a science of the artificial that could be expressed fully as statements of declarative logic and formalized as a scientific, measurable practice. Simon's claim was, of course, the manifestation of a larger cultural change. It was the beginning of it was close to the invention of the electronic computer. The prospect of cheap calculations was there. Society was starting to get used to the idea of computers as part of the civil society and not just as war machines. And it has also something to do with a shift in the kind of education that architects and designers were getting at universities. Simulations were starting to be key sites for scientific inquiry, and slowly designers and architects were starting to catch up. Simon's claim thus helped create an image of design practice guided by objective criteria, quantitative analysis, repeatable results. Instead of thinking of design as something that is learned through practice and through doing, Simon's view enabled the view of design as something that could be formalized as a symbolic language, something that could be computed with and transmitted. From dealing directly with materials to articulating knowledge using symbolic systems, from apprenticeship and repetition to the acquisition of formalized knowledge in symbolic form. This move helped design gain the kind of academic legitimacy that was elusive to trade schools. Suddenly, design was a legitimate member of the university system. And of course, in architecture, we can find links to a contemporary image of the architectural design as something that is quantifiable, performance-based, data-driven, and so on. In contrast with an image of architecture as driven by the subjective intuition of individual architects. However, this scientific image of design entailed a paradox, which is the paradox I want to discuss today. Conceived as a quantifiable and objective practice, design could be imagined as a process of optimization and as theoretically independent from societal actors, materials, skills, and craft. Supported on advances on computing, Simon's propositions sought, through abstraction, a divorce, a dissociation of design from its specificity. But as historians and sociologists of science have taught us, scientific representations and computer technologies are not neutral nor objective, but express worldviews and inscribe propositions for social and technical reconfigurations of practice. So probing and challenging these narratives is crucial to engage with the important questions about architecture and the built environment today. This is a habit of mine that I seek to instill or to nurture or nourish in the book, Builders of the Vision. And it tries to cultivate this mindset for design as it relates to technological change. Basically, to take technological narratives where certain futures are presented as seamless, as inevitable, and examine them, to use Keller Easterling's words, to focus less on the stories and more on the observed dispositions. Despite the stories about efficiency, cleanliness, and seamlessness that often go with technological systems, what we call computational design is in fact a rich tapestry of crafts indigenous to a culture of technological research linked to the Anglo-Saxon university and to the alignment of industrial, military, and academic vectors unfolding throughout the second half of the 20th century. Rather than thinking of computing as a technical subfield of architecture or as an instrument, we may see it instead as a connective tissue that encompasses key cultural and material aspects of contemporary design across fields. So if I do my job right today, you will see how contemporary architecture may have more to do with airplanes and projectiles and missiles and fighter jets, helicopter wings and ship hulls than with its classical and modern predecessors. Why is this important? After all, we know other archaeologists of the digital. We know about Greg Lin, we know about Peter Eisenman, we know about other men, usually white men, with claims to pioneering computational design in architecture. These are very valuable accounts, but they also outline a void. To understand this void, we have to look outside architecture into the rapidly changing landscape of technological research taking place since the postwar years in the US and in the UK. Optic pens, radar screens, military research contracts, mathematics, disciplinary tensions within research universities, punched cards, software, cathode ray tube displays, servo motors, aircraft and manufacturing, political doctrines, the travel of ideas, equations, and people across continental and institutional boundaries, non-rational Bezier curves, numerically controlled milling machines. All these are not passive spectators, but engaged actors in a rich web that also redefined what it meant to design, to represent, and to be creative. This web constitutes a new condition, which I want to describe as infrastructural. A socio-technical infrastructure of a scale and intensity that the field of architecture has yet to fully confront. Another way of saying this is that software systems today resemble telegraph lines and railways more than what they resemble drafting tables. They are no longer tools, but infrastructures shaping the way we practice design and imagine the built environment. Software and other numerically controlled systems are increasingly invisible or infrastructural, and yet condition growing portions of architectural and design production. John Walker, the CEO of Autodesk, the company that makes AutoCAD and Revit, understood this very well since the early 80s. Even without using the word infrastructure, he wrote, "Never underestimate the power of a widely distributed tool." Granted, he was probably talking about the power of this tool to make him immensely rich. But that is perhaps besides the point. What Walker's Foucauldian statement does help suggest is that we have yet to grapple with the infrastructural scale of design technologies, and thus a shift of perspective is in order. Seeing design technologies as infrastructural allows us to recognize the new forms of work, the new forms of craftsmanship, the new forms of social organization that accompany their design, adoption, operation, and maintenance. Taking this view will help us engage critically with the production of the built environment and to avoid deterministic or mystifying positions about technology. I will focus now on a site that I think is crucial to understand the intersection of disciplinary sensibilities between mathematics, engineering, and architecture in the postwar. It's the architecture machine group. It's something that I'm sure many of us have read about or heard about. It's a research group started by Nicolas Negroponte and Leon Groisier at MIT in 1968. And as some of you may know, it's the direct ancestor of the Media Lab, of the MIT Media Lab. So it's an important site that shaped the expectations and shaped the aspirations of those of us who are interested in technological perspectives concerning creative practice. But to trace the intellectual archaeology of this place, of the architecture machine group, we must go back to the origins of CAD itself. Origin stories of computer-aided design inevitably point at Ivan Sutherland's Sketchpad system as the first example of interactive computer graphics. Presented as part of his PhD thesis in 1964 at MIT, Sketchpad was in fact a transformative achievement, encoding many of the features that we see today in CAD interfaces. It had rubber banding, it had instantiation, it had stress analysis, and other features that contemporary CAD systems have. And yet, Sketchpad did not emerge from a void, nor from the desire to automate drafting. And these are two common mistakes. Computational ideas about part design and manufacturing have been circulating at MIT laboratories since at least the 1940s, specifically around efforts to create the first numerically controlled milling machine, which is what this picture shows. By 1952, these efforts had succeeded as a result of the collaboration between John Parsons, an aircraft manufacturing executive from Michigan, and the MIT Servomechanisms Laboratory, directed by Gordon Brown, and housed within the Department of Electrical Engineering. It was actually John Parsons who had the idea of making an automated milling machine, and he had an Air Force contract in order to build it, and he called the MIT laboratory to help. However, the MIT engineers gradually displaced Parsons' authority and took control of the project. But that's a story for another day. Engineers and technologists whose name few architects know, like Gordon Brown, William Pease, and Douglas Rose, devised languages, devices, and theories for the representation and manipulation of information for manufacturing. What is very important about this moment is that by drawing together information about geometry, materials, and machines in the new symbolic space of software, the Servolab team laid out the foundations of the first theories of computer-aided design. And what we see here are early 1950s pages from a manual for the first programming language involving numerically controlled machines. However, by the end of the 1950s, members of the Servolab had discovered that the so-called automated process was so laborious that it called the efficiency of automated manufacturing into question. The machine was driven by punched paper tape, and preparing the tape demanded hours of tedious translations between manual drawings and machine-readable information. They started to wonder if computers and data processing could be used to automate aspects of the design stage as well, so that they could get rid of the blueprints altogether. And I really like this image because this image shows how, the top part of the image shows the original process where the designer gives the images to a draftsman, and then the blueprints are used. Okay. Yeah. So the designer here, there's only a couple of steps between the designer and the machine. Maybe I'll just use the. Well, it's okay. But as we go increasingly in the more automated stages of the process instead of getting simpler, it gets more complicated. So it shows how there's an explosion of skills associated with the automatization of numerically controlled fabrication. So this is the origin, this anxiety about automating aspects of design production was the origin of what came to be known as computer-aided design. However, the Servolab researchers were not designers, and they knew very little about design, so they brought other people into the picture. They invited faculty members and students from the Engineering Design and Graphics Division of the Mechanical Engineering Department at MIT, and started a series of joint meetings between January and May of 1959 at MIT. The expanded team comprised the original Servolab members, led by Douglas Rose, who's the person sitting down in the picture, and a team of designers from the Design and Graphics Division, as I mentioned, led by Steve Kunz, the person standing up. He was then an assistant professor, and also comprising Robert Mann, T.M. Bauman, and Timothy Johnson with Larry Roberts. Those of you who know about the history of CAD know that these are the key names in that history. The computer-aided design project was funded by 3 successive contracts with the US Air Force between 1959 and 1970, and it was jointly led by Ross and Kunz. The CAD project was funded with the goal of improving manufacturing efficiency for the military, and their motto was, in all capitals, more Air Force per dollar. This combination of disciplines, purposes, skills, and sensibilities was key to defining the first technologies and theories of CAD, as we will see. But the CAD project was also at the root of MIT's history of post-war sponsored research that resulted in the foundation of the MIT Laboratory of Computer Science in 1975, the precursor to the MIT Computer Science and Artificial Intelligence Laboratory, CSAIL, and later of the MIT Media Lab. In 1963, the CAD project was placed under the larger interdepartmental initiative Project MAC to develop and foster man-machine problem solving. At the convergence of wartime efforts in graphic interfaces, such as the colossal SAGE radar defense system, servo mechanisms, and the accumulated knowledge about network computing from the time-sharing project. The computers themselves are essential to this story. Project MAC was planned around the state-of-the-art IBM 7094 computer, which was a time-shared machine to which around 100 people on the MIT campus had access through remote consoles. So, the screens and the optic pens and the new data structures and forms of interaction that emerged from these early days, connecting automated manufacturing with design, did not simply seek to replicate the work of draftsmen and shop operators. This inscribed an ambitious theory of design, which was supported on 3 key conceptual pillars. First of all, there was a new idea of the image as a structured artifact, a new tectonics of design representation. These engineers realized that images were no longer pictorial representations, but rather engineered artifacts that were only made possible by their numerical structure. And that represented a big break with earlier traditions of representation in design. The second one is a new division of labor between man or human and machine, which speaks of a cybernetic view of design as a human-machine interaction endeavor. And the third theoretical pillar of this first CAD theory is a humanization of the computer as a perfect slave or collaborative partner of human designers. So we can see it's not yet the Steve Jobs move about making computers personal and individual and making them be like you, but there's an impulse in these early days, this post-war computing sensibility about turning computers from war machines into things that could be assimilated to creative partners, something that is in the service of a civilian enterprise, basically. These 3 pillars that I just discussed are visible throughout the documentation of the project, the technical memoranda, the papers that they wrote. They theorize design as a kind of language processing and as an iterative process of representation and analysis, where a creative stage in which a design representation is created was followed by a mechanical stage in which the representation was tested against different metrics, such as mechanical stress and overall structural performance. The leader of the design team in the CAD project, Steve Kunz, believed that the creative stage was better suited for humans, while the mechanical stage could be successfully automated. This view was one of the concepts guiding the project's technical efforts. In a 1963 memorandum, Kunz imagines CAD in cybernetic language as a system joining man and machine in an, quote, intimate cooperative complex, a combination that would use the creative and imaginative powers of the man and the analytical and computational powers of the machine, each with the greatest possible economy and efficiency. So this is important because these engineers were not merely technicians solving a predefined problem, but rather they were design theorists and they were philosophers who sought to reimagine design as a computational process. Steve Kunz His contributions to CAD are massive, and his life intriguing. He was a self-taught mathematician. He never finished a degree. And he was a talented designer who worked in the aircraft industry for many years. He was a key figure in the development of computer graphics. And something I discuss in detail in the book, he was one of the key design theorists of the 20th century. Also crucial, the CAD project confronted two epistemological cultures of design and representation. The mathematically inclined Servo Lab, whose members were inclined to see themselves as scientists, and the experienced designers from the Design and Graphics division, whose teaching and research were practice and project-oriented. In the Servo Lab's worldview, exemplified by the highly abstract and language-oriented approach taken by Ross, design could be imagined as a process of representation. Everything could be calculated if it was adequately represented mathematically. In contrast, for the experienced designers from the Design and Graphics division, design was more of a verb, an open-ended and essentially human activity. The phrase computer-aided design, as opposed to computer-automated design, which defined the project's subsequent research efforts, first emerged from these meetings, reflecting the designer's view that computers' role was to be supportive of, rather than a replacement for, humans. This theoretical debate between augmentation and automation inscribes a disciplinary conflict. If during the 1940s and the 1950s the ESL had automated the work of milling machine operators by shifting their work from their shop into the programmer's desk, they now sought the same shift in the drafting room. For Koons, Johnson, Mann, Baumann, and the other designers involved in the CAD project, asserting the complex nature of human decision-making was a way of affirming their social roles and professional identities as designers, resisting the Servo Lab's imperialist impulse to recast them in the symbolic language of computing. The tensions between these two sensibilities is visible all over the archival materials of the project, as well as in the accounts of some of the survivors. In a series of notes written shortly after one of those seminar meetings, Koons uses music as an example to consider the boundaries of creative practice. This is perhaps one of the first instances of making a case for human authorship in the digital age. In the spirited note, authorship remains with the human even when a computer is automatically generating a new piece. In doing so, Koons defines creativity as distinctly human, consisting of reflective operations construed to be outside the capacity of the computer. This debate also reflects a shift in higher education in the United States after World War II. It's a move away from applied case-based learning into more theoretical forms of training and research. This new culture of university research assigned a greater value to knowledge that could be verbalized, mathematically encoded, computed with, and transmitted. The activities of drawing, as we all know in this room, the activities of drawing and making, which are crucial to design and design education, do not lend themselves easily to codices, to universal postulates, or stable theories. In contrast to other disciplines like mathematics, electrical engineering, and later computer science, the messy and applied practices of design and architecture appear to be far from the new order and from MIT's very core. What is at stake is no less than the place of design and creativity in the university. Koons was never offered tenure at MIT and left in 1969 for a full professorship in Syracuse. This was difficult to understand for his students, a truly distinguished list, including pioneers such as Nicholas Negroponte, Ivan Sutherland, Robin Forrest, Timothy Johnson, and Larry Roberts, and many others. Some of them saw him as a father. When I asked Tim Johnson about this, he said, "Koons turned me on. He turned Ivan Sutherland on, and he was worth several full professors." Nicholas Negroponte and other former students expressed similar thoughts in interviews. While Kunz was never offered tenure at MIT, he held various other positions in universities in Colorado, Utah, Michigan, and Harvard. He died in Boulder in 1979 at the age of 67. The CAT project researchers were the first to systematically explore and theorize design as a human-machine endeavor. But they were also theorists and public intellectuals who debated and promoted their ideas and technologies, shaping the contemporary imagination and practices of design. Now let's see how an architect used software to theorize experimental scenarios involving architecture, the environment, and the city. Nicolas Negroponte needs little introduction. He is well known for his work as a chairman of the One Laptop Per Child Foundation and as chairman emeritus for the MIT Media Lab. What is less known is that his influential career as an academic, technological entrepreneur, and futurist evolved from a different, if connected, set of concerns linked to the early days of computer-aided design and to Steve Kunz. Negroponte and Kunz first met in the spring of 1962 in one of the architectural geometry courses Kunz had developed for the architecture department at MIT. A few years later, in the spring of 1966, when the computer-aided design project was working full steam ahead, Negroponte attended the course Computer-Aided Design, a class in which Kunz introduced both his method for describing three-dimensional surfaces and the fundamentals of matrix algebra behind perspective projections in computer graphics. Following the course, Kunz became a co-advisor for Negroponte's thesis, a piece of architectural research exploring computers as machines for simulating perception. After finishing, and after a very brief stint at IBM of approximately 5 days, Negroponte accepted Kunz's invitation to teach his analytical geometry course in mechanical engineering department. Soon after, Dean Lawrence Anderson hired him as a faculty member in architecture. This is the architecture machine space in Building 7 at MIT, where a great deal of Negroponte's work took place. This is a research group that he co-founded with his former advisor, Professor Leon Greuser. And it was a platform to explore the potential of computers to transform the fields of design, architecture, and urban planning, and that during the 1980s would expand and evolve into a new department and academic discipline, the MIT Media Lab. If Kunz used to say that computers and numerically controlled machines were the perfect slaves of designers and artifacts, perhaps we can think of the early work of the architecture machine as a series of playful and systematic rejections of this theme. The group's early projects and texts portrayed computers less as slaves and more as partners, as old friends, or as playful, ethical robots that would enable individual users and communities in the design of their own environments. This portrait of computers as human-like agents of social and environmental change is discernible even in projects that predate the group's formation, such as Urban 5, where Negroponte explored natural language as a vehicle for human-machine collaboration in design. A common theme of these early projects is the desire for a more adaptable environment through a technologically enhanced and user-driven practice of design, and for dwellers to bypass the authority of architects, planners, and politicians in order to democratize design. Urban 5 is itself an experimental computer-aided design system, comprising a cathode ray tube screen, a keyboard, and an optic pen, and a small console with several controls, notably including a panic button. The system was capable of receiving text commands from the user, interpreting them as geometric and spatial constraints, and then calculated and displayed three-dimensional responses on the screen. If the system was unable to match the input to a response, the program would request further specification. In case of conflicting constraints, the program would display gentle alerts on the screen, such as the one we're seeing now. However, Urban 5 did not fulfill its designers' expectations because of its inability to enact what Negroponte thought were the attributes of a truly adaptable architecture machine. Playing is learning, but Urban 5 has not been sufficiently sophisticated actually to frolic. Instead, it has inexhaustibly printed garbage. Another project is SEEK, a machine involving a family of gerbils, a computer vision system, and a robotic arm jointly reconfiguring an artificial habitat. And when I asked Nicolas about this project, he said, "This is probably the stupidest thing we ever did." SEEK shows, but it's interesting, what is interesting about SEEK is that it shows that the architecture machine group was looking for a double emancipation. It was looking for the emancipation of the computer slave from human tutelage, and also looking for the emancipation of ordinary people from professional designers, who are often construed in the group's literature as unnecessary middlemen. This rhetoric of democratization has problematic outcomes as well. The Hesdorfer experiment, for example, has 3 black men from Boston's ghetto area, quote unquote, communicate with a computer in order to find out about their urban needs. The subjects didn't know that the machine was not really an artificially intelligent computer, but instead simply a keyboard and a printer that were operated remotely by one of the researchers in an adjacent room. The book celebrates the fact that during the experiment, the subjects did not type uncalled for remarks, quote unquote, and argues that they engaged the machine in a way that would have never taken place if the interlocutor was a white planner or politician. So the neutrality attributed to the machine here is worthy of notice. In the Hesdorfer experiment, the machine is presented as a neutral device, helping researchers conceal their personas, their politics, and the politics of the experimental setup, and more specifically, their whiteness. By the mid-1970s, urban and architectural concerns were no longer the focus of the group's work. The group leaned instead towards systematic exploration of new human-machine interfaces. These included gestural controls, speech recognition, pressure-sensitive displays, responsive surfaces, and digital video as a random access medium. The Aspen movie map, which is what we are seeing now, from 1978, for instance, is described by media theorist Lev Manovic as the first use of the computer as a meta-medium, a space where different forms of time-based media coexist, giving origin to a new communicative form. What we know is that through their projects and texts, the Architecture Machine Group defined the blueprint of a still expanding landscape of research, professional, and cultural practices. The transformation of the group into the Media Lab in 1985, with its massive footprint on the current imagination of design and technology, provides concrete evidence of this. So as you can see, there's a connecting line between the first milling machine, the CAD project, the architecture machine, and the Media Lab. So technological projects linking the 1940s and the 1990s, basically, and the present. And they're all connected. They're all framed within a historical and cultural narrative of finding civilian uses to what, until the late 40s, was understood to be a war machine, the computer. So the questions about computing and the debates between augmentation and automation, between embodied interaction and symbolic manipulation, illustrate the convergence of different and sometimes conflicting philosophies of research at MIT. Is human intelligence a kind of symbolic manipulation, or is it an embodied conversation with the world? Can design be convincingly reduced to analytical problem solving, or is it better understood as the open-ended exploration of ever-changing alternatives? How confidently can we draw boundaries between the technical and the creative? What is truly computable about design? And what is architectural research? Many of us in places like MIT, Carnegie Mellon, the IAAC, continue to seek intersections between the specifically architectural and the technological, and still grapple with these questions. And this is probably okay. We carry these intellectual legacies, these aspirations. How to do so in a way that is both critically astute while acknowledging the aesthetic capacities of technological infrastructures. I think a lot about this, since I'm also shaping graduate programs and training researchers in computational design, and in a context where I hope that we can combine technical and critical sophistication. But what this lineage, from numerical control to the Media Lab, shows, what this lineage shows is that even experimental or impractical technologies carry a blueprint of their makers' time, desires, and questions. While unsuccessful as planning tools, Urban 5 and the machine in the Hesse-Dorfer experiment projected design as a collaborative, quantifiable, and evolving dialogue between always adapting humans and machines, there is no doubt that these were provocative propositions. But this history also shows some pitfalls. As the CAD project and the ArcMax sought to humanize the computer and turn it into a perfect slave of design, it also obfuscated its complex ties to its own makers. Imagining the machine as a human hides crucial areas from critical scrutiny. Crucially, the imaginaries, assumptions, and interests that go into their very design. Also, the aspiration of the democratization through technology, so key to the architecture machine, inscribes what I call in the book the paradox of participation. The notion that without the technologies, people are not fit to participate, thus casting political agency in itself as a technologically mediated process. This way, what is intended to be a bottom-up process is in reality a top-down operation, the deployment of technology, which in the case of the OLPC computer ended up literally throwing computers from a helicopter. Despite the fantasies of human-like robots, it is the technologists whose face is concealed, just like in the Hesse-Dorfer experiment, who colonize the space of design. These imaginaries are alive and well today. Perhaps the most important idea I have tried to convey today is that while most design technologies discourses are premised on the idea of reducing the time and the skills needed to design and to manufacture, this time and these skills are in fact transferred into an infrastructural economy of technology design, production, maintenance, and operation that all too often remains outside the focus of architectural and design scholarship. To finalize, I will share a few thoughts. They are just points for conversation or working hypotheses as I try to define what kinds of architectural research are fit to our age. We must create new critical and speculative tools and vocabularies to make visible and engage critically with these socio-technical infrastructures. We must develop new methods for data collection and visualization, allowing us to see design from a new perspective as a collective socio-material and technical process. If we are to create truly creative, radical, and astute architectural research, we must demystify technology and challenge its dominant image as an inevitable autonomous force. Instead, we must see computation as an indigenous practice, reveal software histories, the ecologies of knowledge developing around large and interdisciplinary technological projects, the alignment of governments, academia, and industry around nation building and narratives, the popular imagination of technology and design, and the artistry of technologists and engineers. A premise of this lecture has been that as architects, we should not only be concerned with the production of form, but also with the critical investigation of and intervention in the larger forces and systems that shape the built environment. We shouldn't see this as a dilution of the discipline, but as a recognition that the production of space is only possible by the alignments and misalignments of complex ecologies of agents, humans, software, professions, materials, skills, machines, and that this is a rich context for both creativity and analysis. Thank you.
Thank you, Daniel. I couldn't subscribe many of your statements, especially the last one. I wonder, I have a few comments, but I prefer if anyone has a question from the audience, wants to throw a question to Daniel. Yeah, sorry,
I can wait.
I was looking there and I can see my...
I can wait for your comments first. Okay, thank you. A very inspiring lecture. A lot of the technologies that the era of Negroponte were envisioned as being kind of like the future, such as virtual reality, augmented reality, and other kind of like robotics, other technologies that are now actually actively integrated in architecture, research, and industry, are transforming the way we conceive and we design buildings. Augmented reality particularly and virtual reality have actually transformed a lot the way we perceive buildings, because we stopped looking at them from a bird's eye view, but we're actually looking at them from within and outside the space. On the other hand, the more kind of like, let's say, hardcore theoretical concepts of artificial intelligence, artificial life that were also envisioned back then are now mostly integrated in places like Google or Apple, and they're actually targeted into money making. Do you think that there is a space in architectural discourse of incorporating that now acquired knowledge?
Yeah. I imagine that as artificial intelligence algorithms become more pervasive, they will end up being introduced in software systems, and they probably are already in a very insidious and perhaps almost imperceptible way in very pedestrian sort of kind of Revit Autodesk kind of functions. But your question is so interesting, and I have the same question, and I wanted to share that I asked the same question to Nicolas Negroponte once, and I said, like, Nicolas, well, you were here, you were in this moment where these technologies, you and your team developed all these interesting visions, and yet the impact of these technologies on actual architectural practice hasn't been that strong. And as you've seen him, he has a great talent for very kind of short and provocative answers, and he said, if you think that the architecture machine was about architecture, then you haven't, so you didn't get the point. I don't remember the exact wording, but it was something to the effect that it was never about architecture. The greatest impact that we had is the iPhone, and that's what that's how he put it. Of course, it's a provocation a little bit. It's trying to say, yeah, these ideas were not intended to affect architectural practice, but I wasn't very satisfied with that answer, because they spent a couple of decades talking about architecture and bringing very progressive ideas, or what seem to be very progressive ideals, into architectural technologies. So I think it's an open question. I think it's one of the reasons why it's a sweet failure in a way. That all the work of the architecture machine is provocative, but it also failed to deliver on the promises of a better, more humane, more interactive, more democratic environment, at least at the architectural scale. Yeah.
Does anyone has a question? Yeah.
Thank you for this speech. I think it was very interesting. And you talk about designing technology in infrastructure scale, maybe in urban scale or global scale. I think it is really interesting. And in this case, how do you define new ecosystem? Who are the new actors? Government or softwares, citizens? Yeah, is it bottom up or top down?
Yeah.
Thank you.
Thank you. That's a great question. I think Autodesk and Adobe and all of these big players in the world of software production are comparable to those companies like the British Railroad Company, who are laying out the railroads in the 19th century all over the world. They are the ones who are specifying how information gets produced, managed, exchanged, and legitimized. And I think they are incredibly important. I think that's what I was trying to convey, that the way in which software systems condition the production of knowledge and the production of design forces us to adopt a larger frame. So one of the things that I would like to convey is the importance of incorporating the software side, the software engineering, into critical studies of architecture and critical studies of creative practice.
Any other questions? Before I make some comments? No, I wanted to recap on basically in the beginning of your lecture and also in the last, because it's actually the ones I think they're very important connections. No? And then I think that you are making a very strong point, blaming somehow the military, and I want to the military industry as probably the activator of many technological developments. I would like to know if you take this as a positive or negative, and also I want to comment on. You probably talk about the last 50, 70 years, but actually if you think about the development of cities and the expansion of the Roman Empire, basically accelerated, basically before the industrialization was the biggest urban expansion probably that we have seen in history. Also, the food technology that Napoleon's troops had actually allowed Napoleon to win the war because they could store food longer than their enemies, and the fighters had more energy. Also, in the First and Second World Wars, actually, most of you're talking about post-war, I'm talking about the pre-war, like, all the polymers, plastics were developed, the microwave oven was invented also thanks to a military experiment. It was an accident. So I think I want to, retake the idea of the military industry and the conflict as a trigger for human creativity. And somehow I want to think about the future. Is it going to be when we really screw up this planet and that challenge of going somewhere else is going to make the next big advancement that we have seen in the last 50, 60, 70 years?
Wow. And, it's a very difficult question, but let me say a couple of things. So, I don't think it's. I didn't want to convey the idea that there's something fundamentally wrong about the military or anything like that. Obviously, but it's obviously a fact that. This technological landscape was produced as a result of the war effort, and that one can choose to see this from at least two different perspectives. And one is to take the view saying, oh, it's the epistemic legacy of the technology sort of tainted by war. That's certainly a way, but I'm not interested in moralisms. The other interesting perspective that one can extract from that fact is that these technologies that we use today were funded by the public, right? It was the military, but it was really American taxpayers, right? Funding these results, and in the current political context where any idea about the public is under such rabid attack by different political actors, to recognize that things like the internet and CAD and computing were publicly funded technologies I think is an interesting point. I think it's an important point to make. Concerning the other side, the other part of your question, yeah, I totally agree. I didn't want to suggest that I was doing a global history of technology or anything like that. My research is confined to 1949 to 1970, most of it, in part because I think there's parallels to be drawn precisely between the projects that you mentioned, the infrastructural projects of the 19th century, as I mentioned, the railroads and telegraph lines, etc., and the establishment of computing and software infrastructures. So definitely, like all those examples that you put are super interesting, and I see them as very valid confirmations of the way in which we humans have started to exert a larger influence on the planet and develop infrastructures of different kinds. The difference with these infrastructures is that we usually don't recognize them as such, right? Especially in architecture, especially in architectural pedagogy, where we tend to frame software as a tool. So I would say, like, yeah, AutoCAD, it's just a tool, or Revit, or Grasshopper. Well, it is and it isn't, right? Because the way in which this tool works, as John Walker reminded us in that citation, saying that never underestimate the power of a widely distributed tool. The tool stops being just a tool, and it starts becoming a language. It starts becoming an infrastructure, and it starts exerting a sort of conditioning influence over the landscape of practices that it channels. That's not to sound deterministic, but we need to learn to develop an eye to see how those influences take place. Yeah.
And I was saying, like, I was also interested in the last part of the lecture, in which you actually talk about design interventions, and probably I want to stress that point a little bit more. And actually, it's connected with your very last comment. So, how are those design intervention strategies, and how do you operate with the tools that you know that are not just tools in order to design that interventions?
Yeah, I think the few points that I was trying to pound home, as people in the US say, was that we need to develop new critical tools and vocabularies to address the infrastructural scale of this technology. So right now, one of my lines of work is developing software systems that allow us to capture data on how large collectives of people communicate as part of a design process. So that visualization that you saw in the end actually maps the work of the resolution of thousands and thousands of design conflicts that were produced during the production of the coordination of a building, right? So I'm interested in developing tools to see those ecologies. I call them design ecologies, large collectives of people connected through these infrastructural systems of software, exchanging information, and I'm interested in seeing how that landscape of data can tell us things about how we design things. That's one thing I'm trying to work on. Yeah.
Any very important questions that we're missing? Someone wants to make? No? Okay. Daniel, thank you very much. We invite you for some beers. Thanks.